Hello, my name is Tamara and I'm from the Education and Outreach team here at Geoscience Australia. Throughout this video, I will highlight the importance of critical minerals to our society, help you become more familiar with the 2D map datasets within the Geoscience Australia Data Portal, and how you can explore these datasets in the context of critical minerals, and especially how to use this in your classroom. So let's start off with some background context. So a mineral is defined as a naturally occurring inorganic solid with a defined internal structure and composition. So another way to describe it is you can describe it by how it relates to rocks. So a mineral is the building blocks of rocks because it takes one or more minerals stuck together to make a rock. And each mineral will have its own specific physical and chemical characteristics, and this is how we can use them for different purposes. So to learn more about some mineral properties, and especially some of these physical and chemical characteristics, you can explore the Google Arts and Culture page that Geoscience Australia has created called Identifying Minerals, and there'll be a link down in the description below. But some other important key definitions is around a critical mineral itself. So, a critical mineral is a metallic or non-metallic element or mineral that is essential to modern technology, economies, and national security. And the key difference between a critical mineral and a strategic material is that they have the same sort of basic definition, but the risks to the supply chain is what distinguishes them. So critical minerals have a risk that their supply chain will be disrupted, whereas a strategic material doesn't have that same vulnerability. And we'll discuss a bit further as to what some of those risks could be to the supply chain. But the other key word that we need to go through that will come up in this video is ore or ore rocks. So an ore rock is a rock that contains elements or minerals that are valuable and that they are economic to extract and process. So for example, in Australia, we have bauxite, which we mine, and it's a key ore rock, and we use it to get aluminium. So we have lots of rich bauxite deposits across Australia. So though it is important, it has a plentiful amount of it across Australia that it's not considered a risk to its supply chain. So therefore it would be a strategic material rather than a critical mineral. And that's that key distinction there. So why should we care about critical minerals? Well, they play a massive role in everything to do with our everyday lives, including our modern technology, like phones and computers. It's a big part of our future, looking towards green technology, like solar panels, wind turbines, and electric vehicles. There's lots of medical applications already being used for sterilized tools or specific implants going into the human body, as well as things to do with security, both in the small scale at your home to the larger scale security, and even transport. So everything from buses, trains, cars, and aeroplanes all require critical minerals to be made. And it's important to note that the specific elements or minerals that are listed as critical minerals has changed over time. So as technology develops, it requires a different set of ingredients or components to make them up, and that gets more and more complex as the technology gets more complex. So for example, around the 1700s, the most critical minerals would have been carbon, calcium, and iron for what was the technology of the day. Whereas now where we are at and continuing to the future, we're looking at a much larger list of critical minerals to cover the wide amount of technology we have. So to learn more about the critical minerals that you can view in Australia and what we deem to be our critical mineral list, we have that full list on the Geoscience Australia website, and you can also see some of the applications of these critical minerals. Additionally, if you want to do more of a deeper dive into how these different minerals are used in modern technology, especially green technology, there's another Google Arts and Culture page about that. And again, as before, all of these will be in the description below the video. But coming back to that critical mineral definition and highlighting the risks that can affect it and what can impact that critical mineral supply chain. So what I recommend is that when you are introducing this topic to your students is that you get them to brainstorm some of these potential risks that could impact it. But I have provided a list here for your reference for you to then do further research in your classroom environment. I will focus on the first two risks on this list, which are geopolitical instability and geological scarcity, as they are the two most, I think the most important, but also the most relevant to the global system of critical minerals as we discuss it these days. So when we look at geopolitical instability for an area, this plays a massive role when it comes to the access and the distribution of critical mineral resources. So this can be affected by many different things, including war zones, political relationships and trade agreements, and it can even be something to do with ethics. So moral obligations or different countries' laws may determine whether it is ethical to access that resource from that country. So these factors can apply to the source country where it has that raw material, or it can also be from the country that processes that material. So some countries will do both. They'll process the raw material after extracting it, whereas other countries like in Australia, a lot of our materials are extracted here but then processed in other countries. So we may not have any geopolitical instability affecting that part of the supply chain, but maybe the country that processes could have that problem. So that's how these can all tie in together. So a really important example of a critical mineral impacted by geopolitical instability is cobalt. So cobalt, as of 2023, 70% of all cobalt resources globally was produced in the Democratic Republic of Congo, or DRC. And so this image here shows you an example of that ore rock where they extract the cobalt from. It also contains several copper minerals as well in there. And the leftmost image represents the metal cobalt form once it's been processed, that raw to the processed material. So though there is industrial mining sites across the DRC, a lot of artisanal mining occurs. So this is the unregulated small-scale mining which is often undertaken by the locals in unsafe conditions, and there has been some examples of child labour being used in this particular region, allegedly. Now, third parties will often come into this area and they will buy this raw material off the locals and will often exploit them by by giving a small amount of money to the locals, but then gaining a much larger profit by selling it on to the groups that then actually process this. So due to the overall unethical mining practices and unsafe conditions, as well as more broader geopolitical instability in the DRC region, the cobalt supply chain is at a very high risk, despite the fact that there is a plentiful nature of it. Despite how much is in this country, it's other factors causing that risk. The second key risk I wanted to cover today is geological scarcity. So this is not having enough of deposit in your country that contains the resources you need, or it could be that even if you do have that deposit, it is not at a high enough purity for it to be considered an ore rock. So Australia has a wide range of critical minerals, and you can see just a few of them on that map there, and this is the critical mineral map from 2023. And we can see that there are several mine deposits as squares and operating mines in the circles and triangles with a wide range of commodities across the country. And I'll dive a bit more into this data layer inside the data portal shortly. But a key thing to note here is that this is just the current resources that can easily be found at the surface. But there's still so much we don't know about Australia's geology below the surface. So some of the major scientific work happening at Geoscience Australia is using different surveying techniques, including geophysical data like magnetic data, geochemical analysis, and looking at a whole wide range of different data sets that can be overlaid over Australia to get a better picture of what's happening below the surface. And this is really crucial to better understand the critical mineral potential across the country. This is really important because even if you had the exact same rock type and the same age in a similar location, it doesn't mean that they will be considered ore rocks. The mineralization potential often is affected by these other processes, and often long-term and multi-stage processes. So it can make it really complicated. And sometimes to get to that higher degree of purity, you need to have multiple levels of either things being leached away to leave a residue, or for things to be concentrated inside to get a key mineral that we're looking for. So by understanding the system as a whole, we can better identify new potential sources of critical mineral and strategic material or rocks across the country. So with that in mind, we're now going to explore the Geoscience Australia data portal so we can use surface geology and elevation datasets to better contextualize the deposits for critical minerals across Australia. So I have the link here on the website and on this slide, and it will also be in the description, but you can also Google Geoscience Australia data portal. So when you load it up, it's going to look something like this. Now we are going to click into a different persona on this website. So we're going to click on the little person symbol in the top right corner and click down to the education, community and education persona. The reason we recommend this persona is that it has a smaller list of all the data sets available on this data portal, and these are targeted to resources we have created in the education and outreach team here, as well as just simplified language around how to use this, so it's more friendly for your students to use. I'm going to show you some navigation tips so you know how to use this. Similar to any other mapping-based portal, you click with your left mouse button and drag to change your view. And you can zoom in and out by using the scroll wheel on your mouse, or you can use the slider provided on the right-hand side to zoom in and out. We're going to be focusing on Australia today, and that's where all our data sets are being loaded into, so that's going to be our main emphasis. You can click on the left-hand side here, the About tab, and this gives you more detail about how this portal works, what each of the little symbols mean if you forget at any point, and gives you a bit of a guide. Additionally, if you need extra help, there are a whole bunch of additional smaller tutorial videos in the little question mark help button on this top right side as well. But we're going to dive straight into it and load our first 2D map data set. And we're going to do that by clicking on the Layers tab in the top left corner. And we're going to go down to the second tab, which is Map Layers, and we're going to go to our first data set, which is going to be under the Geology tab. So Geology, and as you click into each one, it will change to red, so you know you can follow along each step. So we go Geology, Surface Geology, National, and then the Geology of the Surface of Australia. And once you hit a data set that you can load, this new menu at the bottom will appear. We're going to click on the last black button that says Add to Map, and this will start to load our data set onto the map behind me, as you can see there. The other thing we're going to do is, because this data set is quite complex, we are going to click on the Legend tab. Now, it gives you a small preview here, but it is too small for us to see on this particular data set. So the easiest way is to right-click on that image and select the first option, Open Image in a new tab. This will allow you to see the full legend in more detail, so you can get a better picture of what's going on. I'm going to talk through how this legend works before we look back at that data set to give you a better idea of how to use this. It is a little complex, but it's split up into different categories to make it easier for you. The top section here are considered the youngest rock units in the area for Quaternary and Cenozoic aged rocks. Now, this is mostly made up of loose sediments, some young sedimentary rocks, and some young volcanics, so anything less than 66 million years old. And each of them will have a color, and they'll have a code associated with them. For down this bottom section with the brighter colors down here, this represents the older rock units. And these are typically going to be solid rocks versus some of the looser sediments in the younger section up here. How this bottom section works is it's split up by age and by rock type. So on this left-hand side, we can see where it starts with the word Archean. As this goes up, we're going from oldest to youngest. And then each of these separate sections are by rock type. So this chunk here represents all the sedimentary rock examples and their codes. The middle section is igneous rocks, and it's split up between volcanic or extrusive rocks, where lava is coming out from the earth, or intrusive rocks, where magma has cooled inside the earth. And then you also have metamorphic rocks over here, from low to higher grade versions. So each of them will have that description. And the way that the little codes work, they're a little small on the screen, but basically the code tells you what age it is plus the rock type. So for example, JS here represents a Jurassic aged sedimentary rock. So you can use a combination of colors and codes to identify things on the map. So if we go back to that map and we just hide the legend and our layers tab for the moment, we can see an overall picture of what Australia's surface geology looks like. So noting again that surface geology means it is only the topmost layer representing the geology we can see, and this is at a national scale. So this is covering a large area. We can see overall that there's a lot of bright colors in different parts of the map which represent those older solid rocks, but there are massive chunks of Australia that seem to have this paler, younger rocks sort of covering over the top of some of those older rocks we can see. As we zoom in, we'll start to see that some of those codes will appear, and it's a bit easier to see what each individual color represents. And the cool thing about this data set is that it can also zoom in to a second, more detailed version of this map. So currently we can see this whole area is just saying it's CZU, it's one rock type, it's all just Cenozoic aged sediments of some sort. But as soon as we start zooming in more, we see this color change and this more detailed map appear. We keep zooming in, those codes will come up and we'll get a better picture as to what is exactly happening in that area. Noting that this is still at a 10 to 20 kilometer scale. So this is still very big picture. So if you want to know exact details about surface geology in one area, this will not give you that level of detail. It's giving that broader picture of what's happening. So that's one limitation of this data set to be aware of. So now that we've got a better picture of how the surface geology data set works, we're going to load another data set. We're going to go back to that layers tab in the top left corner, and we're going to load an elevation map. So we're going to click on the elevation and depth, and then we're going to select the very first option, which is Australia Land Surface Elevation Shuttle Radar. And we're going to add to map as we did with the last one. You'll see that this, as a new data set, will load on top of the other. So it'll be two separate data sets sitting on top of each other. And again, we can look at the legend for this to give us an idea. This is a much simpler legend. Basically, how this is going to work is that anything that is white to grey white to red is going to be our highest points, the highest elevation. And anything that is in the greens going down to pale blue is our lowest elevations. And they're all going to be in meters. So if we sort of zoom out and get a better picture of the whole of Australia here, we can see that we have certain chunks of Australia that have quite high elevation in that red, and they represent our mountain ranges. And so that includes like the Great Dividing Range here on that East Coast area, for example. Any areas that are that green to paler yellow sort of colors are going to be our low-lying areas or our basins. And any area that has consistent color all the way across is going to be a flat area. So there's no changes in the elevation, which means that this will be like a plain. And anything that's got a rapid change from like red, orange, yellow, green is going to be a slope. So we can already tell just from the elevation data some landform features, and we can start to get a picture of some of the topographic features. Other features we can identify, especially as we zoom in further, will be any water bodies, so lakes or rivers that are present in that system. So we're going to use a little case study example to test out this elevation data set, and we're going to do it by using another tool in this top left panel. This is called the location search tool. So here we can search for anywhere you want, and in this example, I am going to search for Hobart. Now, as this comes up, it will always come up with the addresses first, but if you want just a general region, like I just want Hobart, Tasmania, we can go down to the places of interest, and this will find that area like that. Now, I want to zoom out a little further to see the wider region around Hobart for this example. So here, we're going to use this elevation data set to talk through some of the topographic features I can see here. First things first, we can see that Hobart is definitely in this lower lying area and it's right on the coastline. All of this here would be water or ocean or river systems. If you weren't so sure, you could zoom out and get a better picture that this is that bay area in Hobart and that would be part of the ocean. We can see that there is that river further up that has reached the ocean and that we've got some inner branches off that gives these sort of squiggly patterns you'll see on the map quite often. We can also see this very high elevation area right here. So this is going to be part of Mount Wellington of that area. And so we can see that there's a clear difference between that elevation and the rest of Hobart, which is further down. So this is just some ways that you can use this data set in this context we're talking about today, but also broadly in geography classes, science classrooms, and other situations as well. We're going to jump back out to see the full picture of Australia again, and we can actually use this little button on the side, which says reset my map position. It looks like a little globe, and that would take you back to this broad picture of Australia, which is really helpful. Now, currently I've shown you two separate data sets that we can't easily compare right now because one's sitting on top of the other. There is a tool we can use which will enable a compare splitter for us to be able to see them in the same location. So just above that reset button is a button with two arrows pointing away from each other, and that's called Enable Splitter. When we click that, we see this little splitter appears in the middle here. Now, we can actually set each data set to sit either side. So first things first, I'm just going to close the legend for elevation because we don't need that anymore. And we can set each data set to be on a different side of that slider. So I'm going to make the elevation be on the left side, and I'm going to make the geology be on the right side. And we can close that tab again. So now, as I drag this across, we can see both data sets being able to be compared in a certain area when we go to explore our case studies further. The last thing we're going to do before we go into some specific case study examples is load in the critical mineral data sets. So this is going to give us that broader picture as to what's happening across Australia. So I'm going to click on the Layers tab, and because we've enabled the splitter, it means it's only showing us the active data layers, which is the two data layers we've already loaded in. On this left-hand side, we're going to click the Filters tab, and we can change that to become all layers again. And that means we can load any new data layers we want at any stage. I'm going to click on that Filters tab to close it again. And we're going to go down to a layers that starts with mines. So mines, mineral occurrences, mineral deposits, mineral resources, and mineral potential. A bit of a mouthful. But under this subheading, we have one called critical minerals. And we're going to click our way through from critical minerals to national to Australian critical minerals. And then we have 4 different data sets that we can load here, each representing critical minerals in different forms. You can load all 4 of these data sets if you want to explore the developing mines and some of the mines that are currently under maintenance, so they're not necessarily operating right now. But I want to focus today on just the mineral deposits. So we know there's something there, but we haven't, no one started mining there yet, or the operating mines. So I'm going to click on the mineral deposits one and click Add to Map. And we can see that's been added into my list of active layers. And we want it to stay on active both. So that way, no matter which way we move the slider, we can always see the critical minerals. I then need to go back through the filters, all layers, and we'll see that we're still in the critical minerals set. And I just want to load in the operating mines down here as well. So now that we have both loaded in, squares are the deposits and circles represent the operating mines. And if I take the legend from the mineral deposits, we'll be able to see what each of those colors represent. So same thing again, I'm going to right click and open it in a new tab. And so we can see that full list here. So all the different colours match across to see which type of mineral deposit it is. Now we're going to just take a moment and look broadly at Australia and just make some observations of some patterns we can see, and then I'm going to help clarify any misconceptions that might come up in your classroom by doing this kind of activity. So if we focus on just elevation, we can see that the majority of the critical minerals are sitting in higher elevations for a big chunk through Western Australia and through the Great Dividing Range area, with a few exceptions that are in the basins. So we can see that there is a couple of these bluey sort of greeny dots through here. And we can see also some on some coastlines might be concentrated. So some observations we can make is that critical minerals tend to be either in higher elevations or on coastal areas or in basins, but not all basins and not all coastal areas, and acknowledging that. If we pull it across for geology, we can see that quite a few of them are sitting in the brightly coloured rock layers, which represent those older solid rock layers, with a few exceptions, those same exceptions from before, that are sitting in that younger units in that same sort of areas we mentioned before, that basiny areas. So if you were to combine these two observations together, you could say that the majority of Australia's critical minerals are found in higher elevations in older solid rock units, with a few exceptions that sit in basins or coastal areas. However, the misconception there is that this is just the current map of critical minerals. It's important to note that there is many more potential critical minerals that are below the surface. So in these basins where there is a lot of this younger rock material that's sitting on top and covering over those layers, there could be critical minerals throughout these areas, and we just haven't looked into that yet. It's harder to observe those if it's got several layers of soil and sand and rocks and other things before you can see below. And we can also observe that not every critical mineral deposit is following the same rules. Some are found in different places to where the rest are sitting, and that's important to note as well. And what we're going to do is we're going to actually go through the first case study example, focusing on critical mineral deposit, and we're going to focus on the anomaly. We've got this cluster of blue dots over here, and if we go and have a look at our legend here, we can see that this represents heavy mineral sands which contain titanium and zirconium. And so what I'm going to do now is I'm going to give a bit more context as to what that means and how these deposits form, and then we're going to come back into the portal to see some of that evidence of what people say this deposit should look like and how it forms compared to what the data sets can actually prove to us. So, jumping back across here. When we talk about heavy mineral sand deposits, a lot of them often contain the same three materials. So we can see them over here. We have got rutile and ilmenite, which are two minerals that contain titanium, and zircon, which contains zirconium. And so these are just some examples of what can be inside of a heavy mineral sand deposit. And for the examples we're looking at today in the portal, this is the specific ones we're going to observe. Now, titanium is a really useful material. It's very strong and lightweight, but it's also biocompatible. So this can be used for many different purposes, including parts of planes, turbines, but also used as artificial hips, as what is shown in the image there, and even some dental implants will use titanium. Whereas the zirconium metal is highly resistant to corrosion, so much so that it's used in nuclear fuel rod containers to sort of hold the actual radioactive material, because it's really resistant to that damage that would come from that radiation. So how these deposits sort of form is that originally these minerals would have weathered out from intrusive igneous rocks that contained them, and then they become these loose sediments, so these sand sort of material. And they will become concentrated over time in the environment through natural density separation processes involving wind and water. And we can sort of show an example of that here. So what I've done is I took a container of sand where half of it was containing quartz-rich sand, typical beach sand. So that's the white material we're going to see. And the rest of it is black heavy mineral sand, which would typically be some of the ilmenite that you can see on that image there. And what I'm going to do is that when I shake this container back and forth, we get to see this density separation process happening rapidly, where this would happen over millions of years or a long period of time in nature. And all of that black material that's much denser than the other quartz-rich stuff becomes settling out at the bottom, and the rest of it sort of would get blown or washed away in nature if it wasn't in a closed container. So this can kind of give you an example of how these processes work. So as we head back into the Geoscience Australia portal, I want you to think about what type of paleo environments that contain wind and water would have been able to facilitate these density separation processes to be able to create a heavy mineral sand deposit. So we already know that we're going to be looking at our case study here down in the Murray Basin, where we've got this big cluster of these pale blue dots. And what we're going to do is we're going to start off by looking at just the elevation data in this area, because it does tell a really interesting story. So we can notice a couple key topographic features that we can highlight. We can see that this is all a green area, so it's low lying, so it's low elevation, but it's also pretty flat. So this is a basin and a plain sort of like area. We can see that there's a little bit of a river through here, but mostly it's inland, and we can see that we've got a coastline here. But one of the most important features to look at is all of these sort of curved lines that are following the coastline shape, going further and further inland. What these are called are either strand lines or beach ridges, and they represent ancient coastlines. So in the past, sea levels have been higher than they are today, and as they slowly increased over time, the ocean would move further inland, creating a different coastline to what we see today. And if you picture a typical beach, we have our main beach area. We've got the waves and the sand area. You have a little ridge at the back, and then you often will have a plain of sand or sand dunes behind it. So you often have to walk past that plain and the dunes to get down to the beach to where you actually can go play in the water. So what this sort of represents is that constant shifting of that beach moving further and further back and moving that ridge line further and further back. And we see that quite a few of these deposits are sitting right along those lines and following that, whereas other parts of the basin don't seem to have that same thing. We can also focus on the geology. So if we bring this across, broadly we can see that this is a younger sediment, but we're not really sure exactly what that is. So if I just pick an area, we've got a cluster of dots up here, and we're going to zoom in further until we get that detailed view. And we're going to see what sort of codes, whoops, there we go, a bit better. We're going to see what codes we can kind of see where some of these deposits are sitting within. So we've got QD for a lot of these areas here. Seems to be the main deposit we can see, as well as maybe a little bit in the CZS area here. So if we jump across into our legend, we know it's going to be somewhere up here. So QD seems to be the predominant one, which is dunes, sand plain with dunes, or coastal dunes, which confirms what we were saying before about it being an ancient coastline and that back of beach area. If we're looking at CZS, that's over here, this represents a sand plain. So all of these things seem to be very similar to what we expect. It's that back of area, beach sort of area. So what that tells us is that the heavy mineral sand deposits, specifically in this region, may have been triggered more by wind in that back of beach area, where it would blow away the less dense other sediments around and then would leave behind that concentrated heavy mineral sand deposits. Noting that in this area and also in other parts of Australia, if we do that zoom out look again by doing our reset button, we can also note that there are several of these deposits in different basin areas and different coastal areas, for example, through this west coast in Western Australia. So it doesn't always have to be wind-based. Other ways that these can be concentrated is through alluvial, which means river-based systems. It can be deltas, where you've got that moving water. It can be the water from a beach with the waves. Lots of different ways that these can concentrate. So if you want to dive deeper into some heavy mineral sand deposits, you can choose different areas around, use that geology and that elevation to give you context as to what the past environment may have been like, and even if the current environment is still the same environment. So we noticed here that this was ancient coastlines moving back, but some of these might just be forming on current coastlines as they are today. But now what we're going to do for the very final example I want to show you is show you an example of a strategic material that's important to Australia. So I'm going to jump back to the slides to give you a little bit of context. Now, we mentioned a little earlier about bauxite. So bauxite is an ore rock that we refine to get alumina, and then from alumina we get the aluminium metal that we use in every day. And so that's that same picture we had before of those two materials. Now, the important thing about bauxite is that it is a sedimentary rock, and how it's formed is by weathering aluminium-rich rocks. And this has to happen typically in a tropical or subtropical environment because you need a lot of rainfall. Rainfall and water is the most important thing that concentrates this into an ore rock. And how it does that is over millions of years, that rainwater will leach away other materials. So often this will be silica or that quartz-rich minerals, and leaves behind the aluminium-rich material. And this residue of all this sort of stuff gets concentrated, and it also starts to cement together to make up this bauxite rock. And we can kind of see all those little nodules sort of coming together and how these are able to combine in to make these rocks. Also notice that it's quite orange and some reddy tones throughout it, as a lot of these rocks can also contain a bit of iron as well. But what we're going to focus on when we jump back into the portal is looking at one final data set we're going to load in. Because this is not a critical mineral, we have to load a different data set to show a strategic material. But we're going to focus on far north Queensland, where there's some really famous bauxite deposits and mines in that area. So to do this, what we're going to do is we're going to click on our Layers tab again. And because we're not focusing on critical minerals at the moment, we want to hide these layers just for now. So to do that, you can either remove it, or easier, you can just change the opacity of that layer so it's at 0, so you can't see it. So I'm going to drag this slider so that the opacity is at 0 for the mineral deposits and for the operating mines. So now we're back to just seeing our elevation and our geology if we use our slider. We're going to click on filters again so we can see all the data layers. And the layer we're looking for is called operating mines. So it is under the mines and mineral occurrences, but it's not under the critical mineral tab. So we're going to go back to the mines overarching tab, scroll down, and we're going to click on the mines, mining projects, and mining activity. And then we can see the next data layer is operating mines. Now we want national scale, and we can see that data layer right there. So we're now going to add that to map, and we're going to see all these dots coming back in. And again, we want it on active both so we can see it no matter how we have the data layer. Now for this one, we're going to, again, click on the legend, and we have a whole bunch of different colors, and all of these are the same circled like dot because they're all operating mines. I'm going to right click and open up that tab. And so we can see here that for the legend, we've got a couple different things that are distinct to what was used in the critical mineral one. We do have still some heavy mineral sands and some base metals that might overlap, but things like copper and iron are really important minerals and materials, but we have so much of it in Australia that it's not considered a critical mineral. And it's the same with the bauxite for aluminium. So this gives you a wider range of different ones that aren't just purely defined as critical minerals if you're looking into some case study examples for in your classroom. So bauxite is going to be orange in color. So we're going to jump back to the map, and we're going to go looking in the northern part of Queensland. Whoops. And as we bring that across, we can see that right up here. There's a whole cluster on this most northern tip of Queensland. So if we know a bit about our geography, we know that the further north we go in Australia, the more tropical our environment's becoming. But we can also see that this is right on that coastal environment as well, so there's a lot of water interactions we can see. And if we zoom in to see what the geology layer is, each of these are sitting within the CZL layer. So again, we're going to go over to our list. We know C, so it's going to be up here for Cenozoic. And for CZL, we've got this really funny term up here. We've got laterite, which basically just represents weathered or soil or top part material. So this is not quite sediments where it's not like a sand, it is like weathered material. And it's even got an extra classification. So this is describing what it contains. So this is the ferro. There's a word represents iron. So this is an iron-rich weathered material as well. So we can see both of that sort of in there. So what this is telling us as we look here is that this is sitting inside a rock layer that is highly weathered, is full of iron, but is also full of aluminium rich material, which is why we have this bauxite deposit forming right here. So both of those together paint the same picture as what a description for that deposit would be. So this is a really good way for you to go exploring in different areas across Australia to see where critical mineral and strategic materials are and why they might be forming in certain places in Australia but won't form evenly all across Australia. And that's a really important concept to teach your students. It's one of those situations where it's easy to think it's everywhere, but the rock type, the climate, the environment, the elevations, all these different things play a really big role as to the context as to where critical minerals are going to be found. But if you want to explore this any further, we do have some activities that will be linked in the description below this video, as well as you can explore more things on our website and look at our education pages. But thank you for watching today.